The game you're seeing is called Duality, and it was made in 3 days for the 5th GMC Jam. I struggle to believe it, but it's actually been 13 years since I made this in GameMaker 8.1. It was an experimental project. It's a labyrinth game where you have to figure out how to get to the exit. Each level takes place inside a small box, and to get to the exit you have to shift the gravity of the room so that new paths open. Needless to say, using a 2D room editor for a game like this is impossible. So, during the 72 hours of the jam, I also made a custom level editor. This enabled me to view the level from all angles, letting me plan out the rather complicated paths the player would tread. I've made a lot of custom editors for various kinds of games over the years, most of them for tiny jam games. I may be outnumbered here, but I'd argue making a level editor is as fun as making the game itself. Keep watching and you may learn a thing or two about making your own level editor for your games. Hi, I'm Snitter, and this video is a part of a video series about my 3D platformer game, for which I've made videos about things I find interesting, like platformer physics, shadows, dynamic clouds, blinking stars, character animation, a complex finite state machine, black holes, kickable footballs, and clusters of grass. But even after working on this for nearly 5 years, oh my god, has it been 5 years? I'm still using GameMaker's built-in room editor. It's time to do something about that. This video will not require that you watch the 13 other videos to follow along, but it will assume you have some familiarity with the basics of making 3D games in GameMaker. But if you don't, well, I hope you still tag along for the ride. For the camera movement, I'm going to use a technique I described in another video of mine. It allows me to freely rotate the camera without having to worry about gimbal lock. Gimbal lock is a common problem when using angles to control the camera, or when orienting anything in 3D space really. Let's say I can control the orientation of this plane with 3 angles, which is what the built-in function matrix build takes in as arguments. One angle controls the yaw, one angle controls the pitch, and the last angle controls the roll. If we then change the pitch so that the plane looks straight up, changing the yaw does the exact same thing as changing the roll. We've basically reduced the 3 degrees of freedom down to 2 by simply aligning the angles a particular way. This is what's called gimbal lock. But what if I told you there's a way to avoid this while still using the built-in functions? I'll switch from storing the angles directly over to storing their velocities, so that the sliders now control how fast the plane should rotate around the given axis. Then instead of setting the plane's matrix to whatever comes out of matrix build, I use it as a transformation matrix to continually transform the plane's matrix each step. When multiplying the matrices in this order, you can think of it as applying the transformation in the camera's own local space and then transforming the result to world space. This means that we completely avoid gimbal lock, since we're not dealing with any world space axes anyway, and the plane can rotate freely no matter its orientation. So if I give it the same setup as before by making it face straight up, changing the yaw angle now actually makes it yaw around its own local up axis. There is one problem with continually multiplying matrices like this, and that is numerical instability. Over time, the floating point errors add up, and the matrix may end up with a weird scaling or skewing. Luckily, I have a function for removing all skewing and scaling from a matrix, so I can just apply this after the multiplication, and we should be good. So here's my code for controlling the camera. It's pretty much the same as the code for controlling the plane, except I've had to switch the axes around. This is because the camera starts facing directly up along the z-axis, unless I rotate it minus 90 degrees around the x-axis. And once we have the world matrix, the view matrix is quite simply its inverse. So to recap, this is what happens when you look up and to the side with a camera that has gimbal lock. And this is what happens to my camera. The next obstacle is figuring out where in the 3D world my 2D mouse coordinates actually point to. This has 2 steps. First, I have to convert the mouse coordinates to a 3D ray. Then I have to extend that ray and figure out where it intersects the level geometry. The first problem, finding the mouse ray, is what we call in the industry a solved problem. Oh, by the way, yeah, I'm not really in the industry. This is what I actually do for a living. By solved problem, I mean I have a function for it. It takes in the view and projection matrices and spits out the 3D starting point of the ray and the 3D vector pointing in the direction the mouse is pointing. What we want to use this for is to find the point where the ray intersects the level geometry. Unfortunately, when the level consists of just a flat plane, this is simply done by solving an equation. We can set up the general formula for a ray, which is ray origin plus ray vector multiplied by some value t. By changing the value of t, we can find any point along the ray. Right now, we're specifically interested in the value of t where the ray equals the z value of the grid. So by setting up an equation where the z value of the ray is equal to the grid, we can solve for t. Rearranging that, we get this equation for t. Then we can use this value to find the x and y position of the mouse grid intersection. Let's draw a little red sphere at the intersection to make sure it's correct. So now we can actually point with the mouse and have the editor figure out where on the grid my mouse points to. However, this is not good enough for an actual 3D level editor. At least not for mine. When I place an object into my level, I want the ray to collide with that too, and not continue through to the grid underneath. I would like to check for ray intersections against many kinds of shapes, not just a flat plane. For this, I will use ColMesh, which is a collision system I've made myself. You'll find a link to it in the description. ColMesh contains functions for doing simple 3D collision checking and ray casting against various kinds of primitives, and it's what I use for the collisions in the game. This is how I initialize the ColMesh. All functions starting with cm_ come from the ColMesh system. I'm using a subdivision structure called an octree. This splits the level into smaller sections so that you don't have to check for collisions against the entire level all at once. In the draw event, I cast a ray against the grid first, then against the octree, and then at the end these are the coordinates of the mouse level intersection. Now we can use this for I'll make a parent struct for my editor objects, since I want them to have some variables and functions in common. I'm using structs for the objects, since I find it easier to get an overview, and it will hopefully make it easier to save the level later. I want all the objects to keep track of their orientation with matrices, so I don't need to store their xyz value, it's all baked into the matrix. The parent has a submit function that does nothing, but it's going to be overwritten in the child structs. So here is a child struct. This object is a sphere, so I also need to know its radius. Luckily, I can get that straight from the matrix by checking the length of one of the vectors, since a sphere must be scaled uniformly in all dimensions. Otherwise, you know, it's no longer a sphere. Then I make it add itself to the ColMesh as a CM sphere that also links back to the struct that created it. This way the struct knows which collider belongs to it, and vice versa. This will be useful later. The sphere overwrites the submit function with a function that sets the world matrix and submits a sphere model I've created previously. I could have drawn this with cm_debug_draw, like I drew the red mouse pointer, but then I wouldn't have been able to rotate it. To make the ColMesh visible, I loop through its object list. This contains all the colliders, so to get the struct that created the collider, I have to use cm custom parameter get and then call its submit function. So if I then make a new sphere when I click the left mouse button, I should be able to place objects into the level. Okay, so let's give it a little test, and left click, and there we have a sphere. And let's click on the sphere, and the new spheres are added on top. Now, wouldn't it be useful to be able to rotate and scale these objects after they have been added? In Blender, you have what's called a Gizmo, which appears when you select an object, and it lets you transform the object with the mouse. Using the Gizmo, you can rotate around several axes, you can move the object around, and you can scale it. I like the Blender Gizmo, so I'm going to use this as my reference. Like in Blender, I want 3 crossing rings for controlling the axes one at a time. My strategy from here will be as follows. Figure out which ring is beneath the mouse. This will be used to find the axis of rotation. Find the 2D screen space position of the center of the gizmo. Use point direction from the center of the gizmo to both the current and the previous mouse coordinates. The angle difference between these two will be the angle of rotation. Rotate the gizmo and any selected objects. Profit! ColMesh makes this easier. I can easily make 3 crossing rings by creating 1 torus for each axis. The first 3 arguments are the position of the torus, while the next 3 are its normal vector. Since I want to be able to move the gizmo around as a whole without having to individually move each component, I put it into a container called a CM dynamic. The dynamic has its own matrix, and by changing that, I can move everything it contains in one go. The draw function loops through the CM list the dynamic contains and draws each ring individually. The loop starts at a constant called cmlist.num rather than 0, since the CM list is an array that has a couple of values reserved at the start of the array. Now I want to cast the mouse ray against the gizmo as well. For starters, I'll check that it works by just casting the same ray as we did earlier. If the red ball appears when I move my mouse over the gizmo, that means it worked. And indeed it does. However, I'm not really interested in the precise coordinates of the intersection. I only need to know which of the rings the mouse is hovering over. What I did in my SMF model tool was to render each ring in a different color to a separate surface, and then check the color of the pixel beneath the mouse. But since ColMesh already does raycasting, I might as well just use that. Now that the ray has been cast against the dynamic, it should contain info about the objects it hit. When a ray hits a dynamic, it returns both the dynamic itself and the object that was inside the dynamic. They're both added to a CM list, which, as I already mentioned, is an array that also has a couple of values on its own. So, to find the ring the ray hit, I need to skip the CM list's values, and then skip the dynamic itself to get the actual gizmo that was hit by the ray. This means that mouse over gizmo should now contain either rotate X, rotate Y, or rotate Z. So now that we know which ring was hit, we can start doing the fun stuff, actually making things rotate. Once the gizmo is clicked, I convert its 3D position into a 2D position using this function. Similarly to the mouse vector function, it takes the view and projection matrices as arguments, as well as a 3D position, but it converts it the other way around from world space to 2D window space. With the 2D window space position of the gizmo in hand, I can find the angle from the gizmo to the mouse with the regular old point direction. But I'm not really interested in the actual angle, but rather the change in angle from the previous step. So I also need to find the previous mouse position. I could store this from step to step, but I'm lazy, and I would rather find it right here and now. Subtracting the delta coordinates from the current coordinates should do the trick. The angle difference from the previous to the current step is the angle of rotation I want to apply to the gizmo, and the axis is dictated by which ring was clicked. With this info, I can build a transformation matrix and apply it to the gizmo, and now it rotates when I click and drag it with the mouse. Okay, that does indeed work for the gizmo. Let's try transforming the selected objects as well by looping through them and multiplying their matrices by the transformation. And, that's not what I wanted. So the objects appear to be rotating around their own local axes, and that does indeed make sense when you think about it. There's really nothing in this code telling the objects to rotate around the gizmo, so we're gonna have to work a little more with the matrix. So I need to transform the objects into the gizmo's local space by multiplying by its inverse matrix, then apply the transformation, and then transform back into world space. Applying the matrix to both the gizmo itself and the selected objects should give us the result we want. And that is the basics for the gizmo. I've tinkered with it and polished it quite a bit off screen, and I added quite a few more gizmos using the same principles we just went through. There's a lot of stuff here, so let's break it down. The outer ring lets me scale the object, then the crossing rings rotate around single axes like you just saw. The inner ring rotates around the vertical and horizontal axes at the same time. The colored pins at the core allow me to move it along one dimension at a time, and the core itself allows me to drag it freely with the mouse. The size of the gizmo also stays constant regardless of how far away it is, and I can even select and transform several objects at the same time. What this level editor lacks now is, well, it lacks quite a lot actually, but right now I think buttons is what it needs the most. I put together a simple struct-driven button system inspired by the excellent button tutorial by Zach Banach. You'll find a link to it in the description. It even has collapsible categories, and adding buttons to it is super simple. Let me just quickly add a playtest button. It should be as easy as just copying this and renaming it playtest. And boom, we have a playtest button. But, alas, there is still quite a lot of work ahead of us before it's going to do anything when I click it. But now I can easily add more buttons for doing things like switching between primitives. So I've added buttons for adding spheres and boxes, capsules, cylinders, toruses, and discs. And I can even switch between different kinds of gizmos. So let's add one of each. A sphere, a box, a capsule, a cylinder, a torus, and a disc. Now we do have a problem with the current gizmo, because this outer ring right here, it scales all dimensions equally, and that works for a sphere because, I mean, if you scale one dimension different than the others, which is called non-uniform scaling, then this is no longer a sphere. But a cube doesn't necessarily need to stay a cube. I want to be able to scale each dimension individually, so I added some gizmos that appear when you need them. So if you only select one object, then it checks which kind of object that is, and if it's a box, then it adds these 3 extra gizmos. So if I drag these, I can scale the cube along each axis individually, as well as scale all equally with the scaling and rotation and stuff like that. The capsule and the cylinder, they work the same way. They have these 2 extra gizmos, so this one scales the radius, same with this, while the purple one scales the length. So if I drag that up, look at it go. These 2, the torus and the disc, work the same way as well. I have 2 rings to control. This ring scales the minor radius, while this ring scales the major radius. Editor Snitter here. If you want to learn how to transform a vertex buffer like this without having to rebuild the entire thing, check out this video. Alright, so far I've added camera controls, raycasting, gizmos and buttons. The things I still need to add for this to be even remotely playable are more objects like the player object and gravity zones. Gravity zones are invisible objects that just tell the player which direction to fall, and a system for saving and loading levels. The gravity zones are basically just primitives as well, so I can use the same buttons. I just need an extra button for switching from solid to gravity mode. I struggled for a bit with deciding how to actually draw the gravity zones. I don't want them to obscure the level, so I'll have to throw transparency into the mix, but as you may know, 3D and transparency don't go well together. I tried drawing them in wireframe mode, but I didn't like that. I also want them to indicate which direction they apply gravity, so in the end, I figured I could draw several layers that smoothly move in the direction of gravity, and to avoid obscuring anything, I turn off Z-writing when drawing them. This made it a bit difficult to see how far away they are, but it's fine while editing the level itself. To make them more visible when editing gravity objects, I threw everything I had at it and drew both a transparent primitive and a wireframe model on top. Adding the player object was easy enough. I copied the constructor function for the primitives and just gave it a custom draw function so that it draws the animated player model. By the way, I keep getting comments that people find his face creepy. Like, what? Look at that little goober. Anyway, now that I have my player object, I can make the final push towards being able to playtest. The player and the primitives in the editor are not their actual in-game objects, but rather special constructor functions that are all placed inside a subdivision structure called an octree. This is outside the scope of this video, just know that ColMesh has functions for handling those. The editor octree has an array of all the objects it contains. This is what I want to save. I figured I'd try saving it as a JSON file, since the built-in function JSON-stringify can convert the entire thing into a string, which can then be saved. But I hit an unexpected problem that I really should have expected with this though, in that when loading the objects back in with JSON parse, none of them remembered which constructor function had created them. Apparently this is called deserialization. Okay, no worries, that would have been too easy anyway. But this means I can more carefully build new structs to save that only contain relevant info. Since info on which constructor function created them isn't saved automatically, I'll have to index them myself in an enumerator, and then when creating the save struct, I'll include the type of primitive it contains. I then push them all into the save array, which I can save as a JSON string. When loading the level, it makes sure to use the correct constructor function based on the type variable of the struct. If editor mode is turned off, the constructor function adds the in-game version of the object instead. So with an updated playtest button that saves the level, ends the editor mode, and then loads the level again, we should be able to finally run around inside our creation. Okay, so let's make an actual little test level for the player to jump around on. I'll make a box for the player to start on. And let's make a little obstacle course. Let's place a box over there and orient it slightly strangely, and one there. And if I left click an object, I select it, and if I hold shift while selecting, I can select multiple objects at the same time. That might be a little difficult to stand on. Okay, there we go. Let's add a capsule down here. Let's make it a little longer. There's the gizmo for doing that. We can also make it a little thinner to make it more difficult to actually jump to. Far below, I'm gonna add a planet. Let's add a big sphere and add an even bigger gravity zone. Let's move the cursor to the gizmo. So now I have the cursor at the center of the planet, and that means that I can orbit around the cursor by holding the middle mouse button. Let's add a gravity sphere at the center of the planet and scale it so that it encapsulates the entire thing. Let's add some more geometry to make it a little more interesting. Now I can actually also view the octree. So you can see the green lines denote where the octree is split into smaller regions. Actually, let's make a little tower and place another planet down here. Let's make that a little bigger and add another gravity sphere. I'm also gonna add a gravity object to the middle here. I'll place it there. And let's scale it up. And now we can test. So let's click playtest and see what happens. Okay. Let's see if I can make that oh! Okay, I'm not standing on solid ground, so let's quickly jump over there. Okay, that's better. And let's see if I can make the jump over to the tiny cylinder and jump down there. And now we are affected by the gravity zone. And let's see if I can make it all the way up to the other planet here. So right now, as I'm standing here, I'm affected by both the gravity zone over there and the gravity zone over here, and it averages the gravity directions so that the transition is nice and smooth. Okay. I think the center of the gravity zone is actually outside the geometry, so I can't find any solid ground to stand on. More work remains before this editor can be called finished. It needs more materials than just grass, it needs more objects, it needs more of everything. But this video is long enough as it is, and I plan to make more videos. So please subscribe, like the video, comment if you want to, and share the video with someone who may find it interesting. And I hope to see you around. Snitter out.